Welcome back. In today's video, I want us to talk about how do we actually find the equation of a tangent to a curve, right? So you'll recall what we've done thus far is that we've established that the derivative function is equals to the gradient of a tangent line at any given point on the curve, right? So namely, we said that if we want to find, right, the gradient of a tangent line at any given point on the function, right, we have first principles which tell us that if prime of x, right, which is our derivative function, right, is equals to the limit as h tends to 0 of f of x plus h minus f of x all divided by h, right? So when we get this output, right, of f of x, right, it's either we are going to get a general formula, right, if we use this form of the equation that can give us, right, the gradient of any tangent line. So we can just substitute any x value into the place of x, right, and then we can be able to calculate any gradient at any point on the graph, so long as the graph is differentiable at that point, right? However, if you wanted to immediately get the gradient at a specific point, right, then we would modify this equation. This is also still using first principles. If they wanted you to find the gradient at a point using first principles, which is essentially the gradient of a tangent line at that point, right, we would modify this equation and talk about if prime of a, right, is equals to the limit as h tends to 0, right, of f of a plus h minus f of a all divided by h, right? So this is when you wanted to get the gradient at that point immediately, okay? If you use the top equation, right, you get your general formula for your derivative function, right? And if you wanted to get the gradient at a specific point, you would then substitute your specific a value into your formula, right? So this is going the route of first principles, right? And would only use this route if the question actually says to us by first principle, okay? Other than that, we would actually use the rules of differentiation. And more often than not, when we solve problems, we are actually going to be using the rules of differentiation because they are faster, right? And they give us the exact same output, right? So when we talk about the rules of differentiation, we talked about the fact that we can look at a function, right, f of x is equals to a constant, right? Then if prime of x, right, would equal 0, right? So the derivative of a constant is equals to 0, right? You can also see this represented as d by dx of a constant c, right? And this is equals to 0, right? Then we talked about the very important power rule, right? Which says that if your function f of x is equals to x to some exponent n, right? Then f prime of x is equals to n times x to the exponent n minus 1, right? And if we had a coefficient, right, to this x term, that wouldn't change anything, right? So if you had f of x is equals to a times x to the n, right? This doesn't change anything. F prime of x, right, it's just simply going to be a times n times x to the exponent n minus 1, right? And that's just basically it, okay? And we also looked at the rule that talked about the sum of differential functions, and that is just basically just an extension of the power rule that is talking about if your function is made up of more than one x to the n term, then you apply the power rule to each of those terms individually. Okay, so when we look at computing the equation of a tangent to a curve, right, we need to take the derivative at that point, right? This means that we are finding the value of the derivative function at that point, right? And this is the gradient of the tangent line at that point, right? So this is the important things that you're going to have to remember. Okay. So once you've evaluated f prime of x, right? This is the value of the derivative function. Okay, and what we say is that the derivative of the function f of x, right, at x is equals to some value a, right, is f prime of a, right? This is the same thing as saying that the gradient of the curve f of x at x is equals to a is f prime of a. Okay? This is also the same as saying that the gradient of the tangent line to f of x at x is equals to a is f prime of a. Okay, so all these things mean exactly the same thing, right? You need to understand the fact that when you are calculating the value of your derivative function, right, that is the derivative of f of x at a point x is equals to a, right? That is the gradient of the curve at that point, and that is also the gradient of the tangent line at that point, right? So why are all of these things equivalent to each other? Well, I can explain that to you by using a picture, okay? So when we have our original curve f of x, right, so over here we have an example of a parabola, so this is f of x, okay, right? When you draw a tangent line, okay, to some point, right, a on this curve, so specifically here we've drawn it to x is equals to minus 1, right? When you find f prime, right, of a, right, which is the gradient at that specific point x is equals to minus 1, right, that value is equals to the gradient of the curve itself at that point, right, and it is also equals to the gradient of the tangent line at that point. Okay, this is because when you zoom in, right, so when you take this point and you zoom into it, right, if you see this picture here on the left hand side, right, just look around x is equals to minus 1, right, you can't actually tell the difference between the tangent line and the curve anymore, right? They actually become the same thing. That's why the gradient of the curve, right, is equal to the gradient of the tangent line at that point. Okay, so let's talk about this in a more general form. Okay, so whenever you're asked to find the equation of a tangent line at a point on a graph, right, this is the type of picture that you need to have in your head. Okay, so first of all, if you're looking at a tangent line, and a tangent line is a straight line, okay, so the first thing that you need to have in your head is the famous straight line formula. Okay, so we're going to start off with the fact that we need y minus y1 is equals to a gradient times x minus x1. Okay, and we're going to modify this equation in just a bit. Okay, so we have some generic curve, okay, that we are looking at, okay, and we want the equation of a tangent line at some point x is equals to a, okay, so which means that, okay, along this curve we have some point x is equals to a. That point always has a corresponding, right, f of a, okay, and this notation f of a is basically saying the y value when x is equals to a. Okay, so first things first, right? If we want the equation of this tangent line, right, at this point x is equals to a, right, the first thing we need is the gradient of the tangent line. That's the most important thing, right? If we want the specific point a, right, we can modify this by saying that the gradient of the tangent line, okay, is equals to the limit as h tends to 0 of f of a plus h minus f of a, all divided by h, which is equals to f prime of a. Okay, again, this part is through first principle. Okay, so another way that we can write down to say that we are looking at the gradient at a specific point, right, instead of writing f prime of a, right, we can also talk about dy by dx evaluated at x is equals to a. Okay, so that's another notation that you can use, right? Okay, so that's the gradient of our tangent line. Next, we will need a point on the tangent line itself, and we have that point. That point is the point a, f of a. Okay, so that's our point on a tangent line. So then now we can then take all of this information, right, and substitute it into the famous, right, straight line equation, and what we'll get is that the equation of a tangent line okay, is given by y minus y1, okay, is going to be our f of a. This is equals to the gradient of the tangent, right, okay, into x minus x1 is given by our a value, okay, so a. But we can then make another substitution and go on to say y minus f of a is equals to f prime at a. Okay, so remember that is gradient of the tangent line is equals to the derivative at that point. Okay. So f prime of a into x minus a. Right. And this then becomes the general form of the equation of a tangent line to a curve. Okay. Okay, so now let's go back to this question that we left off from yesterday, right? So this question was not necessarily asking us to find the equation of a tangent line at a point, right? But rather we were asked to find the equation of the line which is perpendicular, right, to the tangent line. Okay, and we set up that equation, that situation yesterday, and we saw that, okay, so initially our first step is going to be to find the gradient of the tangent line at the point x is equals to 2, right? And once we've done that, we'll be able to find the gradient of our line, right, by using the fact that the gradient of the tangent line times the gradient of our line must equals minus 1, right? Then our point A is going to act as our x1 and our y1 coordinate, right, which we can substitute right into our straight line, okay, formula, right. So let's go and actually do that today, right. So this is question 7.4, right. So the way that we would go about this is we would first start with the fact that the equation of our curve is y is equals to x plus 12 over x. Okay, so in order to get the gradient of our tangent line, right, we need the derivative function, right? So we're going to have to say dy by dx, right? But before we do that, let's just rearrange our equation so that it's ready for the power rule. Okay, so that's rearranging y so that it's ready for the power rule. Okay, Now we can say dy by dx, right? So the derivative function of y with respect to the variable x. Okay, so this is equals to, well, the derivative of x is going to be 1 times x to the exponent 1 minus 1, right? And the derivative of 12x to the exponent minus 1 is going to be plus, right, 12 times minus 1 times x to the exponent minus 1 minus 1. Okay, so dy by dx is given by x, well, to the 0, okay, which is essentially 1, okay, minus 12 times x to the exponent minus 2, okay, and we can flatten this out. So dy by dx is equals to 1 minus 12 divided by x squared. Okay, so that is our derivative function done. Okay, so we now have the general derivative function, okay, that can help us to get the gradient, right, at any point along this curve y is equals to x plus 12 divided by x. Okay, so let's do that. Our point of interest is x is equals to 2, right? So therefore dy by dx, right, at x is equals to 2, right, is equals to 1 minus 12 divided by 2 squared. Okay, and if you pop this into your calculator, you get that this is equals to minus 2. Okay, so what does this mean? This is the gradient of the tangent line at x is equals to 2, right? But we only needed this gradient so that we can calculate the gradient of our line. Okay, so that's the only reason why we were after this gradient. Okay, so we know that the gradient of this line that we're looking for, right, times the gradient of the tangent line must equal minus 1. Okay, so the gradient of our line times minus 2 must equal minus 1. So therefore the gradient of our perpendicular line is equals to 1/2. Okay, so now we have the gradient of our line. Okay, once we have that, we need the corresponding, remember, if you look over here, we now have this, okay, and we now have this, right? We now need to evaluate our point A, okay, so we need that corresponding y value, right, because that's the point of contact between these three objects, the curve, the tangent, and the perpendicular line. Just note this line is also sometimes called the normal. Okay, that's just an aside. Right. Okay, so if we let, okay, y is equals to x plus 12 divided by x to equal f of x, right, then we can simply quickly say that f of 2 is equals to 2 plus 12 divided by 2, right? So this is equals to 2 plus 6, right, which is equals to 8, right? So that's f of 2, so therefore a, okay, is the point 2, 8, right? So this is our x1 and this is our y1. Okay, so now we are ready to go into finding the equation of this line. Okay, and now this one is just a straight line. Okay, so it's just going to be defined by y minus y1 is equals to gradient times x minus x1, right? If you want to make this more specific, you can talk about y minus the y value at a is equal to the gradient of our perpendicular line times x minus x at the point A. Okay, so now you're ready to do all your substitutions. So you're going to have y minus 8 is equals to 1/2 times x minus 2. Okay, so we'll have y minus 8 is equals to 1/2 x minus 1, right? So this will lead us to y is equals to 1/2 x, right, minus 1 plus 8, right, is plus 7. Okay, and this is the equation of this perpendicular line right to the tangent at A. Okay, and I hope this is the same answer that you got, and I hope you also found this question quite interesting. See you next time.